Today, we're going to put into practice some of the logarithmic properties that we learned in the previous lesson. In this first example, we're asked to solve the equation, and we get to use the property of equality. This property says that if you have a log with the base equal to another log with the same base, then this part of the problem will also be equal to each other. One of the key things that you want to remember here is that this only works if you have a single logarithm equal to a single logarithm. Nothing in front, nothing below, no extra numbers on the outside. So in this case, I can simply cross out those logs and set negative n equal to 15. To solve, I'll divide both sides by negative 1, and I get n equals negative 15. Now, one of the things that you need to do with logarithms is you need to just double check your answer. You cannot take the log of a negative number. So if your answer, when you plug it in, results in the log of a negative number, then you would have to say that this is an extraneous solution. It doesn't work. In this case, when I plug it back in where the n is, I get a positive number. And so I'm taking the log of a positive, which is okay. Number 2 will be the same type of problem. I'll run through this rather quickly. Log 3 is equal to log 3. Since these are the same, I know that negative x can be set equal to x plus 6. To solve, I will subtract x on both sides, which gives me negative 2x equal to positive 6, and I'll divide by negative 2. So my answer is x equals negative 3. Now I'm going to test it. If I take this negative 3 and I plug it in on this side, I get negative 3, which is a positive 3, and that is okay. Same thing on the right-hand side. If I put the negative 3 here, when I combine it with the positive 6, I get a positive 3. So again, I'm taking the log of a positive number, which is acceptable, and so my answer is correct. In this example, you might notice that there are not any base numbers written down. Remember that if you do not see a base number, it is a base of 10. These are the same, and therefore I can use my equality property. X squared plus 16 is equal to 11x minus 2. Since I have both an x squared and an x in this problem, I know that I'm going to have two answers, and I'm going to try to factor. If factoring doesn't work, I could use quadratic formula. I'm going to get everything on the same side, and I want to do it in a way that keeps the x squared term positive. So I will subtract my 11x and move it over here. I'm also going to go ahead and add 2 at the same time. That means that everything on the right-hand side of my equation goes away. When I combine what I can combine and put these in descending order by exponent, I get x squared minus 11x plus 18. This is a trinomial that can be factored into 2 parentheses. Remember, the x squared is going to break down into x times x, and I'm looking for 2 numbers that can multiply to a positive 18 that when I add them together gives me a negative 11, negative 9, and negative 2. Now you're going to take each factor and you're going to set it equal to 0 and solve. My first solution is x equals 9, and my second is x equals 2. Just like we did before, double check, put them back into the original equation, and make sure that it is the log of a positive number. If I plug 9 in here, it remains positive, so it's okay. If I plug the 9 in here, it also remains positive. I'll double check that 2 also, and it's okay. So I'm going to go ahead and circle it also. In number 4, you might have noticed that we don't have a log equal to a log. We have a single logarithm, but this time it's equal to a number. If you think back to the way that a logarithm is typically written, you have your base, you have this power out here in your number. And remember, if we're looking at things in logarithmic form, we can change them to exponential by using the loop. Base to the power equals the number. So I could solve this logarithm if it was a single logarithm with nothing in front, nothing behind, no extra parts. If you look over here, I need to move something. Hopefully you looked at it and noticed we need to get rid of this -9. So how do we do that? This -9 is multiplied times the logarithm. So we can divide -9 on both sides. Now I have a single logarithm, and I can use the loop to solve it. I'll take my base number, I'm going to raise it to this power, and I'll set it equal to this number. So 7 to the first power is equal to a plus 7. To solve, I'll simply subtract 7 from both sides, and so a is equal to 0. Again, test it. If I put a 0 here, does this remain positive? 0 plus 7 is 7. So yes. Number 5 will be the same type of problem. Again, I have a single logarithm, so I need to make sure that it is completely by itself. If there's any numbers added, subtracted, multiplied, or divided, I need to get rid of them. I'm going to add 5 to both sides. That leaves me with log base 9 of -6k equal to positive 1. Now that I have a single logarithm, I can use the loop to solve. So 9 to the first power is equal to -6k. Divide both sides by -6 and reduce your fraction if you can. So my final answer is -3/2. Again, test it. If I put the -3/2 where the k is, -6 times -3/2 results in a positive number. So I'm okay. I can go ahead and circle my answer. In number 6, you might take a first glance and think, oh good, I can just cancel all the logs out. But you can't. As I said in the first couple examples, it has to be a single logarithm equal to a single logarithm. I don't have a single logarithm on this left-hand side. I have 2. We learned a property in the previous lesson of condensing. We can take 2 logarithms and rewrite them as a single logarithm. We do this by focusing on what is happening between these logarithms. If they are being added, we will change this into a multiplication problem. So since they are both log base 4 and log base 4, that's the first thing that I'm going to write down. Now what am I going to multiply? I'm going to multiply the 10 times the x plus 3, and we'll use distribution to do this. 10x plus 30. Now I have a problem like numbers 1, 2, and 3. I have a single logarithm equal to a single logarithm. So I can get rid of my logs and set the numbers equal to each other. 10x plus 30 equals 61. To solve, I will subtract 30. So 10x equals 31, and divide by 10. So x is 31 over 10. Double check your answer, and it does stay positive in the parentheses, and so I am okay to go ahead and circle it. In number 7, we once again have 2 logarithms on the same side of the problem. Anytime you encounter this, you need to condense these logarithms and make them a single logarithm. This is going to become log base 7, and we're going to multiply 4 times negative x, which gives us negative 4x. Now that I have a single logarithm equal to a number, I'm going to use the loop to solve. 7 raised to the second power will be equal to negative 4x. So I've got 49 equals negative 4x. Divide both sides by a negative 4. So my final answer is negative 49 over 4. Double check it. If I plug in negative 49/4 into the problem, am I taking the logarithm of a positive number? And I am. Let's go ahead and circle it. Number 8 is going to require us to condense once again, but this time we have a subtraction sign between the two logarithms. If you see subtraction, you're going to change this into a division problem. So when I combine these, the logarithm will remain the same, log base 9. You're going to divide the first number by the second. 4x squared divided by 8. If you can reduce this, I would go ahead and do that. 4 divides into 8 2 times. So this is what my problem now looks like. I have a single logarithm, so I can use the loop to solve. 9 squared is equal to x squared over 2. 9 squared is 81. To solve for x, the first thing I need to do is get rid of this 2. And since it's divided, I'll multiply it on both sides. I've got x squared equal to 162, but I don't want x squared. I want just a single x. So I will take the square root of both sides, and I'm going to make sure and add a plus or minus sign on my answer side. 162 isn't a perfect square. There's a couple different ways that you can figure out what comes out and what stays inside. I use prime factorization. If I break down 162, it looks like this. So what am I looking for? Square roots mean that I need something that multiplies times itself. I'm looking for things that show up twice. If something shows up twice, it gets to come out of the square root. If I have multiple things that show up twice, they're going to multiply together. So in this case, a 9 will come out of the square root, but this 2 is going to remain inside. In this last example, we're going to solve it by condensing once again, and it is subtraction, so it will become division. I've got log base 7 of 2 divided by x minus 1. To solve this single logarithm, I will loop. 7 to the first power is 7, and I'm going to set it equal to 2 over x minus 1. I need to solve for x. X is currently trapped down here in the denominator. One way to remedy this is to move the entire denominator to the other side, and we can do this through multiplication. If I multiply both sides by x minus 1, it eliminates my denominator, and now I have an easier problem to solve. I've got 7x minus 7 equal to 2. I will add 7 to both sides, and then I will divide by 7. As I've done in the previous problems, I'll make sure and double check to make sure things stay positive as far as the logarithms are concerned. And they do. So I can go ahead and circle my answer, and I'm done.